So before we can understand a Poisson probability distribution function, you need to understand a binomial probability distribution function. A Poisson is a little bit, it's related, but it's a little bit different. And if you don't understand binomials, you need to go back and look at those first before you think about Poisson. Poisson is a French name, by the way. So we have requirements for for binomial distribution functions. We've been talking about those for a while. Make sure you understand what the requirements are for a Poisson distribution and how it's different. How it's different than a binomial. In the text, the way they describe it, the two things that are different. Here they list the requirements. I'm on page 243. Here they list the requirements, and a lot of these requirements are the same as a binomial distribution. However, there is something different. The two main key things that are different about a Poisson distribution is that a binomial has to have some n. In the problems we were looking at before, we knew it was either 5 questions on the test or 10 questions on the test. But a Poisson probability distribution only has a mean. In a binomial distribution, there is some place where it kind of stops. The Poisson distribution, it could keep on going with no upper limit. It's kind of how my grandpa decided to have babies. He wanted to have kids until he got 2 girls. He didn't say, I want to have 5 kids, hopefully some of them are girls. He said, I'm just going to keep on going until I get 2. And so you think about the probability of not having 2 and probability of not having 2, and there's no upper limit to where that would go. So anytime I'm dealing with some situation where there's no upper limit. So we have a situation here. There's the site. I'm getting this from the U.S. Geological Society. In Oklahoma, they were averaging 1.6 earthquakes of magnitude 3 or higher. 3 or higher means those are ones that you can notice. Anything below 3, you probably wouldn't even know it's happening. So we've got 1.6 earthquakes per year for about a 20-year span. Okay? And first thought, why can we think about this as a Poisson distribution? Again, we just talked about the requirements for a Poisson distribution. When we're talking about number of earthquakes, it's some kind of measurement over time, so time is involved, but it's distributed over time. It's uniformly distributed over time, but there is no upper limit. It's not like I'm giving it 6 tries to have an earthquake and I strike out. Like I was with the, I had 10 tries on the binomial test situation that we were talking about a little bit ago. So there's an unlimited, there's no top end to this. In theory, there could be as many earthquakes as there wants to be. So here's a better situation for Poisson. I don't know what n is. The n doesn't even apply in this situation. If n doesn't even apply, that next question is what is mu and which is the mean and the standard deviation. Well, back when we were dealing with my binomial, we said that the mean was, where'd my paper go? We said that the mean was NP. Well, there is no n when I'm dealing with a Poisson, so I can't really think about NP. Poisson doesn't get it. They don't have an n. So if you think back there, when we talk about a Poisson distribution, it says the mean is mu. You have to be given the mean in this situation here. So think to yourself here, with this situation, what's the mean? And yes, it's right in front of us here. It's 1.6. We're averaging, mean is average, 1.6 earthquakes per year. So in this situation here, I've got mu being 1.6. The standard deviation is unique. Again, there's no n to use for my standard deviation calculation. Here, my standard deviation we just assume is the square root of mu. It's unique. Go read the text as to why that is. Okay, so my standard deviation is going to be the square root of 1.6. And the square root of 1.6 is 1.2649. 1.2649. So here's my mean, here's my standard deviation. Okay, so the first question is, what is the mean and standard deviation in this situation here where we're talking the U.S. Geological Society and Oklahoma? We have all this data for 20 years of existence. Here's my mean, here's my standard deviation. Okay. Next question. If I had 5 earthquakes in a year, is that normal? Now, obviously, if my mean is 1.6, that's a little bit higher than I would expect. It's not here, but would that still be considered a normal year? Think to yourself about what we talked about when we said normal and what kind of a range we used when we talk about normal. If you're struggling for a hint, think about the range rule of thumb. The range rule of thumb is a good idea. Sorry if you hear my son in the background. Well, the range rule of thumb says that 95% of the time I should expect it to be within 2 standard deviations. So if my mean is 1.6 and I venture up 2 standard deviations, that means I'm going to add this twice and I'm going to subtract this twice. I'm going to have to pause.